Good with B. Okay. This is kind of important idea. So this guy experiencing or creating an electric field going that way. This one's creating an electric field going this way. This one's creating an electric field going that way. I don't really care about that one. The y component of this is canceling out with the y component of that. Okay, so all you get is this way. Okay. Have a conversation. Tell them why you think so.
That's the only thing that's different. Because it's d squared. Yeah, yeah, yeah. I don't even know. So you take square root of x equals d squared.
Okay. Correct answer is C. We did the Pythagorean theorem. It's the square root of it. Like this distance here is the hypotenuse. X squared plus d squared equals r squared. We're having r squared, but the square root of that knocks out that squared term. Good? Okay. Thumbs up when it's coming to you. Have a conversation, tell them why.
Do these? No, I didn't say that. That doesn't sound like something I would do. Sorry. Yeah, it's the same deal as like the dubious dictionary uses x over doing hypotenuse.
Okay. Correct answer is D. Dangerous dinosaurs. They're super fast. I want the x component of that. Okay, so I need to use cosine, but that's not an option. That's what I think you're going to find a lot in AP is like, this is what I think should happen, but that's not an option. Okay, so then we have to think, all right, well, stink. How do we do that? Well, this is that angle's that angle, and well, okay, cosine is, I guess, adjacent over hypotenuse, and hypotenuse, well, we established that to be that. So this is cosine. Good at that. Okay. So we can simplify this. So to find, actually, we could simplify that. So this is like to the, oops, sorry, to the 2/3 power. You okay with that? So you have 1 whole and 1/2 for adding those exponents. You get 2/3 power in the denominator. 3/2. What do you call dyslexia when you like flip up and down? That's an interesting one. Anyway, okay. So we're finding the top. We're doing the net electric field. So the X component of the top, X component of the bottom, and the electric field of the middle. So there's the top and the bottom are like symmetric. So here's our expression for what we just developed. It's times 2 because there's 2 of them. And then from this one, this is easy. This is just twice the charge divided by x squared. So we go to that. That is not something to memorize. Don't memorize that. Okay. All right. So using this expression, if we are really far away, have a conversation.
Yes, serious. Where is the source? All 4 charges. That's the net electric field. Okay, 4Q over 4 pi. Oh, the letter after B. Oh, okay, so it's the amount of. No, because the E net is the net electric field. You don't put more charges into the E net that's far away. That's just the net that has all 4 charges in it already. You don't need more 4 charges. What do you mean it has all 4 charges? The E net has all 4 charges. Simon, if E only has 2 charges, has 2Q. Yeah, the 2 for multiplying by the 2 in the X. Yeah, there's 4 charges from E net. Are you guys seeing something?
Okay. Correct answer is, okay, we don't have a definitive, okay, so, which is fine. What I'm about to tell you, you can take this with you, problem solving, the rest of your life. Okay, this is just one example of this tool. Make extreme cases. Okay, what do I mean by that? Make one of these variables infinity. Make one of the variables, like if it's appropriate, negative infinity, or make one of those variables 0. Like, see what happens if you like just crank the knob up, engineering wise. Like, what's going to happen? Okay, worst case scenario. Does that make sense? Like, when you're figuring stuff out, you're like, what would happen if I took it to the extreme case? Does that make sense? Usually the math gets simpler when you go to the extremes, or at least you're looking for the math. If you put infinity in and it doesn't get simple, well, don't put infinity in. Try something else. You see what I'm okay? So here, this is like much bigger. So like the first guess is like, oh, I need to make x infinity. Well, then when I go sticking that in here, like that's 0. That doesn't help. Okay, so we could make d 0, approaching 0. Does that make sense? Like, it's so much bigger that this, well, it could be 1, it could be 2. Yeah, but it's going to be real close to 0 when this is like 3 million. Is that, this making sense? Like the approximation. So this is the beauty of science, and even further. Okay, so I wish Mr. Clumpy was still here, because he just, you guys have probably heard of Mr. Clumpy, maybe. Okay, so he's like, math is the pure science. Like, you all metal it up, like, yes, but we use it to do stuff. Like, and like, so we're approximating. Well, it's 2. Well, yeah, well, that's really close to 0 when you compare that to 1,000,000. But it's 2. You can stick in 2 and stick it in your calculator, see what you get. It's going to be real close to 0. Okay, so approximate. Okay, so if this is 0, this just becomes x, the square root of x squared, so that's x, cube it. No. Cube it, and then the x cancels, you x squared, and we can add these two. See, this becomes 4, and so you get c. Ever see how that happened? Okay, conceptually. Okay, so here's a big, for the AP test, you need to be able to dance between the math and the concepts. I'm going to try to do that. I try to do that justice. Okay. Conceptually, does that ring true? If you pull yourself way away from this, this is going to look like a point charge of 4Q at this location. Kind of like resolution. If you're driving at night and you see a car way down the interstate on the other side, does it look like 2 headlights, or does it look like one bright spot? It's like one bright spot. As you get closer, those headlights start to separate, become distinctive between. But way far away, that's just going to look like a point charge of +4. And that's what that would be mathematically. You all right with that? Yeah. So you see the challenge. Like, strategies of problem solving, take the extreme cases. Okay. conversation.
It's always. So, just think about it. The chart is broken. The top and bottom. No, I totally understand. So it's either B or D, right? And it's not B. But the only distance that matters is the assume my answer is zero. No.
Okay, correct answer is. Okay, so this one, the math doesn't really help you, right? Because you're like, I stick 0 in for x, and it's like, undefined. Okay. That's okay. Pull back. Like, this is like the struggle. Like, okay, my initial line of thinking is failing me. Is there another perspective to look at this? Okay. So then draw it out. So I'm like right there. Okay. This is going down like this. This is going up like this. The x component of these is pretty small and getting smaller as we approach 0. You all right with that? So as we approach 0, the electric fields from these two become less and less significant. We can approximate that, their contributions to 0. So all it is going to be a point charge with a charge of 2 from the center guy. James.
If it's D on both top and bottom, that wouldn't the electric field not be 0?
You're right. There's totally an electric field, but it's going more vertical. Like the Y components are canceling out. Agreed. There is an electric field from this guy, but it's going more and more this way, canceling out with this guy.
So why wouldn't it be 0?
Because there's an electric field from this one who's also playing a part, actually playing a very significant part. If it was just if this one didn't exist, yes, the electric field at that location at 0 would be 0. Agreed. Simon.
So where is it in the map?
Where's what in the map?
How do you get that equation from that one?
You don't. Oh, how's okay.
It's somewhere in there. Why? It's because they.
All right, I'm gonna. That's a valid question. I don't really like. Good. All right, so we made if we made that, we'll make this 1.
Yeah, I know.
Mr. Smart,
Yeah.
you make D basically like infinity, right? Yeah, 'cause it's so much bigger.
Oh yeah.
Think about it.
Yeah. That does it.
Does it work?
Yeah, that works.
Okay.
It's the D zone. D approaches D.
Except for the one on the left, of course. These are the one on the right, not the first.
Yeah. I don't.
Okay.
Sort of. Okay. So here's what I would do. I would just get my calculator out and plug in a really small number here.
It's not. Okay.
Yeah?
Sure.
Because if I plug in 0, that doesn't help me.
No, it doesn't.
And if I plug in infinity, that doesn't help me.
For D, it would.
It like actually gets 2. It gives a coefficient of 2 up top.
Yeah, because if your bottom is going to the limit of 1 over infinity is 0.
Right.
So then.
Oh, yep, it does. Yep. Nice. Aiden. Oh, that was a high five. Okay. All right. So let's look at 2 scenarios where you have 2 charged objects, both point charges, and then we take second scenarios. We take ball 2 and kind of like smear it, kind of like a butter ball, and but the charge is still there. Okay.
So on the last one,
Yeah.
If you like bring the point actually all the way to 0, is there like 0? Like it goes all the way to infinity.
So like the killer with a point charge is it's going to be when you reach the charge. That's kind of like how long is a point? It's like it's not. That's what kind of gets sticky. So you could say, let's go into the object if you want to say there's a volume there, which we'll deal with later. Tell your neighbor. Correct answer is B. Agreed. Okay. There's a greater distance here. This is the closest the charge can be to this one. As you go here, we're getting further away from this point, contributing less force than it would be at the shortest distance. Okay. Check this out. If we smeared it like this, so it is all equidistant from ball 1, then they'd be equal. Does that make sense? See where we're getting? the net force would be equal.
It would be.
Oh, good call. No, yes, good question. Ooh, you're right. Just scratch. I retract that statement.
Well, I think it just asked for the force.
No, force and field would both be less because you have y components now that cancel each other out. Okay. All right. So uniformly charged line. So remember how we had linear mass density or linear density? I didn't really throw in mass in there. Just had a linear density. We're going to have the same conversations with charge density. Okay. Where we have, we're going to still use lambda, sigma, and rho as linear surface charge density and volumetric charge density. Having the same, so instead of saying mass over length, we're going to say charge over length. Okay. Instead of saying mass over area, we're going to say charge over area. Instead of saying volume over area, no. Instead of saying mass over volume, we're going to say charge over volume. So this is charge density, surface charge density, volumetric charge density. Okay. And we're going to do the exact same tricks. We're going to chunk it up into like, hey, we're going to look at a section of this. Like this chunk. Okay. And if we make this a really small little chunk, you got dq over dl. That whole ratio thing. Okay. Same trick. Okay. Which opens a whole slew of different things we can do. Okay. But you've been exposed. You just now, we're deep diving. This is going to be our like point of conversation for the next week or so. Yay. Okay. So it's in units of coulombs per meter. Okay. Here we go to C. Okay. We take the perimeter of 4 centimeters, 0.04 meters, divide that by 8 nanocoulombs, divided by 0.04, gives you 200 nanocoulombs per meter. Good? Here we go. It's a warm-up question. It's a slow on-ramp here. Make you feel good about yourselves. Tell your neighbor. Okay. Get a B. Oh, buddy. Oh, buddy. Oh, buddy, oh, buddy, oh, buddy. Tell your neighbor. Good. Starting you out easy. Is everybody okay with that? Like, okay. So notice how I'm expressing this. It's a small contribution of electric field. Okay. Pretty confident you know where we're going with this. Okay. But we want to pick out, hey, what we want to divide this up into small point charges, which we were then going to add up. Okay. But we first need to be able to identify what the small amount of charge is going to do to that point P. Talk to your neighbor. There we go with B. Or, sorry. There we go with that. I want to get dq lambda times dx. So the left side is identical in all expressions. This is what's being your options. Tell your neighbor. Tell your neighbor why.
Because of trigonometry. I learned in the ninth, actually the 8th grade, how SOHCAHTOA. Well, I didn't want to be untruthful. Realized halfway through my sentence. My bad. I'm sorry. I did not mean it like that.
Okay. Which trig function are we using? Cosine. I want the vertical component. This angle, I'm going to look at this angle from the vertical because this angle is that angle. So I'm looking at cosine of that angle. So A over adjacent over hypotenuse. Good? Okay. Bet you can predict what the next slide is going to ask you to determine. Correct answer is Dangerous Dinosaurs. Okay. This is the adjacent side. This is the hypotenuse. Okay. And this is the hypotenuse squared. It was a square root, and then I squared it, getting rid of the square root. Good? Okay. So, this, my friends, is the small component, the vertical component of this electric field produced by this little point charge. This little infinitesimally small charge located there. Well, what about the one right next to that? What about the one right next to that? What about the, oh, don't they all contribute to the net electric field at point P?
You know what time it is.
Well, you know what to do, kids. Okay, so what we're going to do is we're going to integrate from so here, this is our coordinate plane. We're going to integrate starting at negative L over 2 to positive L over 2. Yes? Not from 0 to L. If we were looking at this point, then we could go from 0 to L. Does that make sense? Charlie?
Did it? I just did it for like 2 times from 0 to L. Would that work? If this works in this
That-
case.
It would work.
You use a class to do that.
Sure. Oh, no. Would not be advised. This is a vector. Direction matters. If we were doing a scalar, that would be a valid. Because all you're going to get is electric fields that are going this way.
Wait, say it again, sorry.
All you're going to get is the net electric field going this way. Well, if you're just looking at the y component, I think, yeah, it would work. That would work.
Say it again.
It would work. because you're just looking at
Maybe not.
you're just looking at the y component. Okay. If you're looking at the x component, that would not work, but the y component would work. Okay. So I am not going to try like. So the cool thing is you have calculators now that can do this for you. You integrate and you get this stuff, and then you plug it in, and then you get this expression. Don't try to do that. Okay. Where the AP test is going, I don't see them making you do this. I see them saying set it up. Even if they do say find the answer, it's just going to be a point. Not worth the time to go through all that based upon what I've seen so far. Okay, so we're just going to use this expression and like evaluate it in terms of scenarios. You okay with that? Big picture, do you understand what we're doing? That's what I'm trying to achieve here. I'm not going to try to achieve integration. Is such a, it works out great in your math textbooks because they've given you problems that are like works. You're set up for success. In the real world, what you do is you write a computer program that approximates it. Okay? All right. So here's your expression that we just came up with. When y is really when y is really big compared to L. Tell your neighbor why.
He died
He was conscripted into the army.
Okay, is everybody good with C? If you made L 0, you get the answer. If you're really far away, you can't distinguish between this being a point charge versus that being a rod. It's just like a point charge. Y away. Okay. So, I want you to set up the electric potential at point P, or whatever point that is. At point P. Don't look here. You know what I need to do? Nope, that's the answer. That's the answer. That's not your setup. This is worth going through. Like, you've got to be able to do this. The setup. I did the hard one. This one's the easier of the two.
Yes. This is what I have. Sorry.
Sorry.
So, the electric potential of a point charge is K, let's say Q, Q over R squared. Not squared, just R. That's point charge. So, what we're doing is taking a little chunk of that, K dq over R. And we're integrating from negative L over 2 to positive L over 2. Okay, do you see the ration? Do you see my train of logic? That is not the answer, but this is how I'm going to get to the answer. Okay. I can pull out anything that's constant. Okay, well, that's obvious. Is R constant as I go down this way? No, I can't pull that out. So I have this problem. So I've got K, L over 2. I'm going to stop writing that because that's just annoying. So I have 1 over R dq. Can I integrate that in this form? No. Okay. I need these units to agree with this unit. They're not even close. I need these variables to agree with each. Not even close. Okay. You see the problems that I need to like address. Okay. So this is where the linear charge density comes into place. Okay. So I can now make that. I'm going to bring it. So I've got K 1 over R Q over L dx. So now I am, oops, doing better. I've now satisfied this condition. These are in meters and that's in meters. Okay, but not the same thing. Okay, so so then I'm going to go, so capital Q is constant, capital L is constant. It's like the whole thing and the whole thing, okay? So I've got K, Q over L, 1 over x squared plus y squared square root dx. Good with that? And that's what I'm integrating. Okay. I'll post an expert TA that'll be due next Tuesday.